There we go. So don't be discouraged by that. I'm not trying to discourage you. Just be prepared to work, because it's going to take work in this class. All right, let's start off. We are going to start with 3.5. Now, I normally, in my history of teaching this class, which has been for a long time, I usually don't start with this section, but I'm doing it because I want to kind of conform to what the other faculty are doing. So I've decided I'm going to start here. Normally, I like to start Cal 2 with really what Cal 2 is to start. You know, the beginning is right. Let's get right into the Cal 2. But we're actually going to kind of avoid that at first. We're going to still do stuff from Cal 1 like derivatives and things like that. So just be aware that if anyone goes back and looks at my old videos from other semesters, I didn't start here. All right. But because I'm going to start here, I want us to at least take some time to talk about what Cal 2 is. All right, and then we'll get into all this stuff. So what's Cal 1 about? Right. So what was Calculus 1? If you had to sum up Cal 1 in a word or two, non-vulgar words. Derivatives, okay, derivative. What's that? Okay, so integrals, that would have been at the very end, right? Yeah. So you saw integration, that's a good thing. Because I can assure you not everyone here saw integration. That's okay, because we're going to start with that. So, Cal 1, tell me about Cal 1 geometrically. Like geometrically, what's that? Optimization, so things like farmer wants to build a pen, you know, right? What else? Anything else that visually? Okay, so let's say I have a graph. What does the derivative mean? How's the derivative of that function related to that picture? What is it? Velocity. I'm hearing different things that are all kind of right. If I said go to this point right here, let's just call it A, and I say right there at that point, the derivative represents what there? Or better yet, what if I take this point here and I say, give me the derivative at that point, what does it represent? Visually, what is it? Slope of the tangent line, right? Do you all remember that? Okay. The derivative gave you slopes of tangent lines. That's basically what it was, right? You started with the limit, and you got tortured with the limit for a long time, and then they said, oh, you got all these formulas, and then you were able to basically take any function, and theoretically, you could take the derivative. But at the end of the day, the derivative gave you a slope of a tangent line, right? And so what we did is later on, we said, all right, well, we have these functions. It doesn't matter what the function is. If we have some function, and we want to figure out where its highest and lowest points are, right? Then we realized that the derivative there at those points was horizontal. And that means that in order to find those points, all we need to figure out where the derivative was 0. And so that's what we would do, right? We would set the derivative equal to 0, or we'd figure out where it's undefined. And so we found maximum minimums of functions. And that's really what the Cal 1 was about. It was about looking at a function, trying to find its highest, lowest points. Even the optimization, that's what it was, right? The optimization, you came up with a function, and then you said, when is it the biggest or smallest? You also did those problems. How about the ones where, like, you have a spherical balloon that's being inflated with a constant volume, right? Call those related rate problems, okay? Again, we were dealing with instantaneous rates of change in things. So what is Cal 2 going to be about? Well, we're going to do more derivatives, okay? We're going to start this class with more derivatives, but we're going to look at some functions we haven't necessarily looked at, or we didn't look at in depth. You may have seen them in pre-Cal. You may have seen them a little bit in Cal 1, but we're going to look at them a little bit deeper here. And then we will get into the new stuff. And the new stuff is going to be, there's a lot of things that we're going to do, but here's one. We're going to go back to this whole idea of a function, right? And instead of looking at the tangent line, the slope of the tangent line, we're going to say, what would happen if we dropped two vertical lines down like this, and we ask ourselves, what is the area underneath that curve? What's that area? Well, I mean, it's a weird shape, right? It's not a rectangle. It's some odd shape. Can we even find the area of that, the exact area? And can we do it for any function? So we'll investigate that, and we'll figure out that, yes, there is a way to do it. And then we'll do something like, all right, well, how about if we have a function and we have some other function like this, and we want to find the area between the two functions, right? We'll be able to do that. And then later on, these things, just like the slope of the tangent line, geometrically was just the slope of a tangent line, but later on it was the, the minimum surface area required to build something or something like that. These will all have physical meanings later, but depending on what branch you're looking at, if you're in engineering or physics or whatever, they all have applications. The area under a curve in a physics application would be like the total amount of work done moving an object from one point to the other. That turns out to be the area under a curve. So we'll look at the area under a curve, and then we get into, we start doing some weird things like, if you were to take that curve, here, I'll just do it on the board here. I'll do a new one. Let's imagine we have a curve, all right, like that. Moved it up too high, I can't get to it. Right? Here's this curve, right? Like this. Let's say I take it and I take it off the page and I straighten it out and I measure how long it is, right? It's called arc length. So we'll be able to measure the length of a curve, which is different than anything that we've done before, right? That's going to require some calculus too. And then we'll start looking at back to this idea of having some curve and having some other curve like this and looking at this area between it. But instead of looking at that area, what we'll do is we'll take that solid, that area, and we'll imagine that we pop this whole graph off the page and we take that area and we rotate it around the x-axis. So if you take that right there and you rotate it around the x-axis, you would get a solid, wouldn't you? And we're going to be able to find the volume of that solid. So you can imagine that there's all sorts of different shapes. Let me try and think of a shape. Like, what would happen if I took this right here and I rotated that around the x-axis? What would I get? Imagine this thing right here comes out and comes around like this and comes back here. You get like a donut, wouldn't you? We'll be able to find the volume of that. And just think about all these different weird shapes in engineering applications, these odd shapes, pistons and things like that. Whatever it is where you would want to know what the volume of it is, but it's not a normal shape, you can be able to find volumes doing things like this. So these are going to be called volumes of solids of revolution, right? Revolution, rotate. And then, we'll do things like, all right, well, if we have this thing that you rotate, right? You rotate that thing around. That's not a good picture. I'm going to have trouble with my donut here. It's not going to be a very good donut. Yeah, it's a terrible donut. Okay, there's my donut. Do you see it been rotated around? All right, so if we can find the volume of that, then we sure as heck should be able to find its surface area too, right? So we can do that also. So there's a lot, you see there's a lot of physical applications to what we're going to be doing with this stuff later. And then we're going to get out of this chapter. We'll get away from all this, and we get to a thing called sequences in series, which is its own animal. It's completely different than all this stuff. But what it really allows us to do is take something like, I'll try and give you the cleanest explanation I can give you. We all remember e to the x? Do we all remember the derivative of e to the x? It's itself, right? It's the only function that behaves that way, other than 0, right? The function 0, the derivative of 0, 0. That's the only non-trivial function that is its own derivative. Well, we will study in chapter 8 that you can take most functions and you can rewrite them in what's called an infinite power series. The dots there mean this keeps on going forever. So if you right now get on your calculator and you type e to the first power on your calculator, it's going to spit out 2.718 something. Okay, that's what will happen. What you don't realize, or maybe you do because you've seen series, that the calculator has no idea what e is. This is actually what your calculator is doing. So if you plug 1 in here, you get 2.718. But if you plug 1 in here, you should get something close to 2.718. It'll be 1 plus 1, which is 2, plus a half, plus a sixth, and this keeps going forever. There's a pattern in this. And your calculator knows that when it gets to a certain place, it goes far enough out that it's within some tolerance, and it spits that answer back to you. All right? But the whole idea that a function can be represented as this infinite list of, these are just powers of x, aren't they? Every one of these is a power of x. That's why we call it a power series. It's a series of powers of x. So because of that, if you can take every function and break it down to this power series, you can really do some amazing things with it. Let's see. Do y'all remember I said derivative of e to the x is itself, right? What would happen if I take the derivative of this? Couldn't you just take derivative of each one? What's derivative of 1? 0. What's derivative of x? What's derivative of x squared over 2? So your 2 comes out, right? Cancels with this 2, and you just have x. And then what about the next one? The 3 comes out, and then cancels here, so the 2 is left on the bottom, and you have x squared on top. Isn't that the same exact thing? I mean, look, these 3 terms are these 3 terms, aren't they? And then the pattern would actually continue if you kept going. So power series and series in general is a major topic here, because computers, this is what computers use. I mean, computers, when you type sine into your calculator, your calculator has no idea what sine is. But sine can be represented with a different power series. And we're going to be able to find a way later to actually come up with a formula to convert any function into its power series. And that's a huge difference. Did any of y'all here in Cal 1 who the different fathers of calculus are, like who created calculus? Leibniz was one. Newton. Those are the 2 fathers of calculus. So there was a point in time where calculus didn't exist. And 2 people, independently, different parts of the world, but at the same time, created calculus from basically nothing. And then they found out, oh, wow, we were doing kind of the same thing. Now, what happened was you know when you write things, you have your own sort of notation. You know when you write things, like if I write 2 plus z, this is the way I write 2 plus z. I strike my z's so I don't confuse them with my 2's. That's notation, right? That's a notation thing that I do. Leibniz and Newton had their own notation for calculus. So when they met each other, like, oh yeah, we're doing the same thing, but I use this symbol, you're using that symbol, because they were making it up, right? It was their own. They could call it whatever they want, right? So they could use their own notation. So they had different notations. So that's one difference in the calculus. But the big difference between Leibniz calculus and Newton's calculus is that Newton was able to come up with the power series, and Leibniz had not done that. So there were problems that Leibniz couldn't do that Newton could do, and so I always say Newton should get more credit. I think Leibniz's notation was better. Like his notation makes a little more sense, but as far as the power of it, Newton's was superior. So, all right, I'm getting off topic. So we're going to do this whole section on series, and it's going to be a weird sort of math that we haven't seen before, because we're going to be trying to show things are true or not true. So we have to run all these tests and use logic, and it's just really, it's not like factor this, where you just do it and there's an answer. It's more involved. You have to prove something, which means that you have to take all cases into consideration, and yeah, we'll see when we get there. So we'll do series, and then we get into some other stuff at the end. We go into some different coordinate systems. We go into polar coordinates. We do parametric equations, so different ways of drawing graphs, and then we're pretty much done. Okay? Sound fun? I know it does. Don't worry, we'll get there. All right, but let's start with this first section, 3.5. So the way the notes work, the whole idea behind having notes for the class is so that I don't have to sit here and write this stuff on the board, and you don't have to write it down either. All right, so we can take our time to try and do examples. So I will read through this quickly. One-to-one functions is where we're starting. Sorry, inverse trig functions. Inverse trig functions. So one-to-one functions. Functions have inputs and outputs, right? You plug something in, it spits something out. A function is said to be one-to-one if every output comes from exactly one input. And a way to do that, a way to check that if you have the graph of this thing, is to do a horizontal line test. Not the vertical line test, the horizontal line test. That's how we check to see if a function is one-to-one. Uh-oh. That's just dialing right there in your pocket like that? Weird. Well, that's all right. Of course, to be a function, every input goes to exactly one output. So you do a vertical line test to see if something is a function. You do the horizontal line test to see if it is one-to-one. If a function is one-to-one, then it has what we call an inverse. And then the images here will show you our basic trig functions. So what I have up here is different than what you have. You have like a static image there. Format. Everyone recognize that function? That's the sine function, right? It's your sine function. It's periodic, has a period of 0 to 2 pi, right? Or a period of 2 pi. Here's my cosine function. That's the difference between the two, right? Is the sine function a function? It's kind of dumb for me to ask that, right? Yes, because it passes the vertical line test, right? You draw vertical lines, you only hit once. Does the sine function have an inverse? Well, does it pass the horizontal line test? If I draw a line that goes across right here, it's going to hit it more than one place, right? So it doesn't have an inverse yet. Same thing with cosine, right? Cosine function is a function, fails the horizontal line test, doesn't have an inverse. How about tangent? Oops, sorry. There's your tangent function, right? Periodic also. Does it pass the vertical line test? Yes, it's a function. Horizontal? It hits here. If I draw a horizontal line, look, we'll use that one that's already there. Hits there, hits there, hits there, hits there. So that shouldn't have an inverse either, right? Cosecant is the reciprocal of sine. There's the cosecant function. Everyone remember how the cosecant comes about? Everywhere that the sine, the red one's a sine. Everywhere that the sine is 0, you have an asymptote on the cosecant function. And then it's just little, like, almost like little parabolas on every one of the max and mins of the sine. So there's your cosecant. Is the cosecant function, does it have an inverse? Now, if I draw a horizontal line here, I'm going to hit it, right? I can spread this out, get more periods if I want here. Okay? Here's secant, same thing. We've got all sorts of problems with secant there. So all of our trig functions are functions, but they don't have inverses. All right, so what we're going to have to do, in order to force the sine function, we'll just start with the sine one. In order to force the sine function to be one-to-one, we have to restrict its domain. So notice there are, oops, that's a typo. There are infinitely many ways we could do this, so we need to agree on one. So look, does everyone agree that if I take the sine function and I restrict it just right there, so let me take the sine function out. If I just restrict it here, that blue part is still a function, right? And it passes the horizontal line test too. So that just restricted part of the sine would have an inverse. Yes? Now the other important thing to look at is the fact that what I picked, this section that I picked, does achieve the entire range of the sine function. It goes from -1 all the way to 1. So I get everything in between, all values. But why restrict it there? Why not do this? Could I have used that one instead? Sure, that would pass the vertical and horizontal line test also, right? Or I could have used this one over here. Or that one, right? Any of those would have worked by themselves. But we can't all be working with different sections, so we all have to agree on one. So the one we agree on is this one, that one right there. So what we wind up doing is we say, look, if we cut off the sine function between negative pi over 2 and pi over 2, look just there, then we'll have an inverse. So we agree to restrict it here. And then here's the definition of the inverse sine. So this little negative 1 up here means inverse. The inverse of sine, if you say the inverse of sine of x equals y, that means that sine of y equals x. So inverses undo the other function, right? And here's our restriction. Now, you might see this notation right here, or you might see this notation. You can write either one, right? Arc sine or sine inverse, they're the same exact thing. I'd say that the advantage to writing arc sine is like if you were typing on a computer, this would be easy to type. That one you have to do your superscript, and so it'd be a little bit harder to type. So what I have here is I've actually graphed. There's the sine restricted between negative pi over 2 and pi over 2, and here's its inverse. And what I wanted to point out with this was how the inverse works, all right, just to make sure everyone's clear on how an inverse works. If I say plug pi over 2 into sine, so what's sine of pi over 2? From this graph, what's sine of pi over 2? It's 1, right? Yes? Sine of pi over 2 is 1. Now, take that 1 that came out of sine and plug it into the inverse. So the blue one's the inverse. If I plug 1 into the blue one, what does it spit out? Pi over 2. So it sends it back to where it came from. That's how the inverse behaves. Whatever a function does, the inverse comes and undoes it. And you can kind of see that from all these pictures, or from this illustration here. All right, so let's find a couple of these here. The way the notes will work, I'll work through these things just like this. And when it comes to an example, I'll switch over to this, and I will work it. So I'm going to do 3.5, example 1. Okay, part A. I want to find the arc sine of 1. So how are we going to find the arc sine of 1? We are not going to grab our calculators. That's not what we're going to do. All right? We are going to think about it. Now, we can do it from the graph, like I just said, right? We just said, what was arc sine of 1? The blue one is arc sine, right? So arc sine of 1 should be pi over 2. But you're not going to have that picture sitting there. So we need a more efficient way of doing it. So this is where we need to kind of test your knowledge of the unit circle. Okay? What do you know about the unit circle? Remember the unit circle? There are all these very important points on the unit circle. And it turned out that if you pick some point on the unit circle, it has an x and a y coordinate, right? If this is theta, the x coordinate was always cosine theta and the y coordinate was always sine theta, correct? On the unit circle means radius of this circle is 1, right? So when we say arc sine of 1, what this really means is sine of what angle, right? This is our question, equals 1. That's what we're saying. So at what angle is the y coordinate, right? That's this. Where is that 1 on this unit circle? Where does it happen? Right up here, right? Because that's the point 0, 1, isn't it? So I'm looking to say, hey, look, that's 1, right? What angle gets me that? So you said pi over 2, right? Pi over 2 is where I get that angle. So that means that theta must be pi over 2, which means this answer, not pi over 2. So that must be pi over 2. And we're done. Agree? Now, if you are very comfortable working with something else other than the unit circle, I'm not here to undo that. I just think from my experience that working with the unit circle like that is probably the cleanest, easiest way to do it. But if you've already like got all the graphs in your head and you don't, don't let me mess that up, all right? I'm just trying to give you something to work with here. Let's look at part B. What about this? So it's asking the same sort of thing, right? That notation just means, hey, arc sine, sine inverse, same thing as that up there. But now I want to know root 3 over 2. So the way I do it is, again, I'm saying sine of some angle, which I don't know, is root 3 over 2. So if I go to my unit circle, I'm asking myself, where is the y-coordinate, right? Root 3 over 2. So where is your y-coordinate root 3 over 2? 60 degrees, right? It's actually 1/2 root 3 over 2. That's at 60 degrees. Is that the only place on the unit circle where your y-coordinate is root 3 over 2? No, there's another one. It's over here, right? It's negative 1/2 root 3 over 2. What angle is that? 120? So which is the answer? Both? Yeah, now this is where that whole domain restriction comes in. What is the domain restriction for the arc sine? You've got to be, the angles that you're looking at have to be between where? We all said we agreed earlier that we would restrict things right here between negative pi over 2 and pi over 2. Where is that on my picture? Pi over 2 is here 0, right? Pi over 2 comes up here. Negative pi over 2 starts here and goes backwards and goes down like this, right? So what we're doing is when we restrict it, we are cutting off the entire left side of the unit circle and saying you're not allowed to be there, which means that the only answer it can be is 60 degrees. If you don't cut it off, though, then you have two answers, and that violates what it means to be a function. You plug something in, it spits two things out. That's not a function. So there's our domain restriction, and that means our answer is 60 degrees, or in radians, what is that? Pi over 3. Now, I would say that everyone in this class needs to be very comfortable with not using degrees. All right, radians need to be very, something that you're willing to work with, because most answers are not going to be given in degrees. Most problems we do will be working with radians. That doesn't mean it's wrong, but you'll see later it can get you kind of lost. There was something else I want to say about that. Oh, if you're going to use your calculator, check your work. You have to make sure you know what mode you're in, right? Degree or radian mode. All right, moving along. So we can do the same sort of thing. We can find the inverse of the cosine function. But to do that, we're going to have to restrict it somewhere else. So I don't believe I went through the whole thing and the development of it, but let's go back to this thing I had up here. I'll bring up cosine. And let me see if I can do this. I haven't tried this yet. Please work. For cosine, y'all agree that's cosine, right? Let me get it on a smaller. Okay. Do you agree for cosine that if I tried to use the same restriction as I did for sine, from negative pi over 2 to pi over 2, it wouldn't work, right? I'd still fail the horizontal line test, right? So I can't use that restriction. So I have to use something else. So what we agree, again, we have to agree on something, is to go from 0 to pi. That will cover the whole range of cosine from negative 1 to 1, and will also pass horizontal line test, wouldn't it? So we just agree now to define the inverse of cosine, we must restrict cosine to 0 and pi. Could it have worked? Could I have done this instead? That side? Just this side. Could I have done that? Yes. but that's not what we chose to do. We all agreed that we would use this right side instead. Understand? All right, so inverse of cosine, restriction is 0 to pi. Now, we can do the same thing with tangent. We can define the inverse of tangent. For tangent, the restriction we use is exactly the same restriction as we did with sine. We won't go look at the graph, but that's the restriction. The remaining trig function inverses can be found in the book, but aren't used much. So if you go in your book, and we're working out of section 3.5, somewhere in there it has a list of the different inverse trig functions and what their restrictions are. All right. Now let's talk about the cancellation property. Since an inverse function undoes a function, right? It undoes it. When we compose the two, they should cancel each other out. We have the following cancellation property. If you try and take the inverse sine of x and then take the sine of that, so you come in with the inverse and compose them together, they wipe each other out, and it just spits the x right back out, right? I always equate it to like a car wash. It's like you got a dirty car, you send it through the car wash, right? And then you got this inverse car wash that you drive through and your car comes out all dirty again, right? So the inverse car wash undoes the car wash. That's exactly what's happening here. But we have to be careful because whatever x is in here, right, the inverse sine of something, right, is going to, you know what, I think I've got these backwards. I need to fix this. You take sine of an angle, don't you? Sine of an angle. These two are backwards. I have my domains flipped. So the inverse sine is going to take a number between -1 and 1 and spit back an angle. And then when you take sine of that, it's going to spit back the number that you originally plugged in. But the big point of this note is just that if you put these two together, they wipe each other out as long as your domain is restricted properly. But all of this can't really be about inverse trig functions. This is calculus, right? So we're interested in not the inverse function, but its derivative, right? That's what we want to know. So if you got this new inverse function, how do we take its derivative? Or how do we find the derivatives of it? So in order to do this, in order to figure out what the derivative of these new inverse functions are, we need two things. You need to be able to remember how to use what's called the reference triangle and implicit differentiation from Cal 1. So let's see if any of that rings a bell. So if we have this new function, y equals arc sine of x, find the derivative. All right, what is the derivative of arc sine of x? Here we go. Does everyone understand that what we just spent the first part of this just talking about what these inverse functions are, and now we're saying what are their derivatives, right? That's what we're saying. And we're going to start with the inverse sine, then we'll move on from there. So 3.5 example 2. Y is equal to arc sine or sine inverse of x. We want to find y prime. Now, if you were to pull up your formulas, now don't do it, I'm just saying if you were to do so, I thought I had downloaded the formulas. There we go. If you come to one of these pages where the derivatives start, here they are, here are the derivatives, you actually will see that the derivative with respect to x of arc sine of x should be 1 over the square root of 1 minus x squared. That's what it is. But the question is, where did that come from, right? Where does that come from? So what I'm going to do is I'm going to develop the formula or create this, show you where it comes from, and then the rest can be done the same way. But ultimately, when you get to a test later on in the semester, when it comes to taking derivative of arc sine or some inverse trig function, there they are. You have them written down. Okay, so let's see how we do it. Well, we're going to first use implicit differentiation. All right, so what I'm going to do is I'm going to rewrite what this means. Doesn't that mean sine of y must equal x. Isn't that the definition of inverse? Right? Or you could also say, if that wasn't as comfortable for you, couldn't you have just said, I'm going to take sine on both sides of this equation? And the left side becomes sine of y, and the right side, what happened here? Cancellation property, and you got x, right? Either way, we should be able to get to that. Now what I'm going to do is I'm going to take the derivative on both sides of this equation and using what's called implicit differentiation. So I like to draw a squiggly line anytime I do implicit differentiation. I don't know why, I've just always done that. It's to let everyone know that's what I'm about to do, implicit differentiation. So what is the derivative of sine of y? Cosine y, and then the most important thing, yes, dy dx. So what happened here was that it was chain rule, wasn't it? I said, what's derivative of sine of something? Well, cosine of that something. Then chain rule says go inside, take derivative of y. What's derivative of y? Well, we're taking derivative with respect to x. So derivative of y is dy dx. So we've got that chain rule. On the right side, we have equals. Now, derivative of x with respect to x is 1. So we just put 1 here. We're trying to find y prime, right? Y prime? That's the same notation right here as this. By the way, Leibniz notation, Newton's notation. Okay? That's just the different ways that they wrote things. So when we're trying to find y prime, we're trying to find dy dx. So isn't this dy dx right here? Okay, so to figure out what this is, I just move that cosine to the other side, right? Okay, so why don't I just do that? Dy dx, if I divide, I get 1 over cosine y, right? And what's 1 over cosine? Careful. Secant, yeah. Secant y, so that becomes secant y, doesn't it? So do we have our answer? That doesn't look anything like what a formula I just showed you, does it? No. What's the problem with that? I started out the problem up here, right? I started out, I'm going to take this, well, I'll leave it there. I started out saying y is equal to arc sine of x, right? And I asked you to find y prime. Shouldn't our answer have x in it? And right now our answer has y in it. Right? So now I'm going to come back here and I'm going to say, look, I need to somehow get that y out of here. I need to make this y have x's instead of y's. So I'm going to go up to where I have a relationship between x and y, which is right here, sine of y. And what I'm going to use, this is that reference triangle part of the problem. I'm going to write down, this is separate work, so I'm going to do it in a different color, I'm just do it here. If I write that sine of y equals x, then can't I draw a right triangle like this? If I call this angle y, then by definition, sine of y is which side over which side? Sine is opposite over hypotenuse. So shouldn't the opposite over hypotenuse be x? And x is the same as x over 1? So I could say the opposite side is x and this side is 1. Now look, what I'm trying to get at here is I'm simply using that equation to draw a triangle that matches the equation. Do you agree that sine, if I draw this, sine of y is x? From that picture? Sine of y is x. Now, why do I care about that? I mean, why am I doing this? What am I trying to replace over here? I'm trying to figure out what secant of y is, right? Well, secant of y is the reciprocal of cosine of y. What is cosine of y, according to this picture? What's cosine? Adjacent over hypotenuse? So secant would be hypotenuse over adjacent. But I don't know what this side is. Well, I don't right now, but I actually have two sides of a right triangle, don't I? So I can find this side, can't I? Do I need to show how to find it? Do you want me to show? Yeah, I'll show. I'll just call that side A for adjacent. I could call it anything I want. The Pythagorean identity tells us that A squared plus B squared equals c squared, right? That's the relationship of those three sides. And so if I take the x squared to the other side, right, move that x squared over, here's a, solve for a, take the square root on both sides, I get that a is what? Square root of 1 minus x squared? Yes? And I don't have to do plus or minus. Why? We're assuming here it's a length, right? All right, so that's good enough for now. I think that's all we need, right? I mean, look, we wanted to know what secant of y was. We used this relationship to draw a triangle. We used the triangle to come up with this relationship between the adjacent and hypotenuse. So secant of y is 1 over this, isn't it? And so our answer back here, coming back to this, is 1 over the square root of 1 minus x squared. Which matches the formulas. Right there. Okay? Questions? Okay, now that we have the formula, we don't have to derive it each time, all right? We have the formula, now we're allowed to use it. So the next example, 2, we're going to use the knowledge of that formula to now figure out another problem. What is the derivative with respect to x, that's what that means, of sine inverse of square root x squared plus 1? What is this going to require? Chain rule. Good. It's going to require chain rule. Ultimately, we have sine inverse of, let's call that whole thing in there u, right? We have sine inverse of something inside of it. What is the derivative of sine inverse of something? We just found the formula, right? If I write it over here, if I have sine inverse of u, the derivative of that should be 1 over square root of 1 minus u squared, shouldn't it? I'm replacing all the x's with u's. That's our new formula for inverse sine. And then what would I have to do after I do that? Multiply that by what? The derivative of u, right? The derivative of u. Now, u is the square root of a polynomial, and so we have to do chain rule on that too. So there's a lot involved in this. So let me write this down. I'm supposed to write 1 over the square root of 1 minus u squared. What was u for us? Square root of x squared plus 1. So what happens when you square that? You get rid of the square root. X squared plus 1? Okay, now that's sitting behind a subtraction. Was it? Wait, it was minus, right? Yeah, it was minus. So it's sitting behind the subtraction. So I'm going to put it in parentheses. It's okay if you distribute the negative through, but I'm going to just put it there just to kind of make sure everyone understands that negative will have to distribute. Does everyone understand that's just the derivative arc sine of u? And now I need to say chain rule times the derivative of u. So what is the derivative of this thing? Square root of x squared plus 1. If that's what our u is, what's its derivative? One half x squared plus 1 to the negative 1/2 times the derivative of what's inside of it, which is 2x. So this is a good point in time for a rhetorical question, right? Isn't that a question you kind of ask yourself? You reflect, you don't really answer it. But how comfortable are you with this, going from here to here? That, again, would be a Cal 1 problem. That's not a Cal 2 problem. Here's another option, another way to write it. Depending on how you learn to take the derivative of a square root. How many of you learned when you take derivative of square root, it's always going to be 1/2, then whatever's there to negative 1/2? How many of you learned it that way? Okay. How many of you learned it that it's just always going to be 1 over 2 square root of whatever was there. Anyone learn it that way? Okay, that's the way I teach it, this way right here. But this is just as well. You get the same answer, all right? There is a little bit of algebra that we can do here to simplify, right? Those 2's will go away. And that x can pop up on top of there. Okay, so let me clean this up. This part right here belongs here. So I've got, what are the only things left in the numerator? What's the only thing left up there? X. Denominator, I have square root of, what did this one turn out to be? It's just going to be x, right? And then you have, don't you actually have the square root of x squared? And then what's the other square root? This one over here. That's, ooh, x squared plus 1? You following that? Pardon me? Oh, hold on. Negative. Yes. Right here. Did I not put that? No, I didn't. This 1 minus x squared minus 1, these will cancel so you get negative. Yes, thank you. And that's automatically should make you go, what the hell's going on here? Well, it's right, but it's not, this is not possible, right? If you square a number it's positive, then you make it negative, then you try and take the square root, right? Something going on. Can we shut that? Does anyone mind just shutting that all the way? Thank you. There appears to be an issue. Do y'all see that? Everything we've done as far as taking the derivative is okay, but we've run into a problem. Everyone see that right there? Okay. Come up here, take a look at this, and tell me why there's a problem with this function. What about, well, I don't know. This would be a good opportunity for bonus right here. But I mean, I'm talking about bonus like someone needs to tell me the problem in the next 30 seconds type bonus. I made this problem up purely to see how you would operate with the chain rule. But there's an actual problem, an issue with this up here, this whole thing, this whole function itself. Tell me about the number right here. That's right. That's right. Okay, look. If I say x squared plus 1, do you agree that that number, the smallest it could ever be, is 1? Yes? And if you let x be anything other than 0, it's going to be bigger than 1. And then you're going to take the square root of that, which is the smallest that could be then would be 1. And then you're going to say be arc sine of 1. But remember, when we restricted, when you're talking about the inverse sine, the biggest number that can go into it was 1 and the smallest was negative 1. So this function is trying to plug things in to an inverse function that are bigger than what it can handle, right? It's beyond 1. And when we took the derivative, that kind of is glaring at us right here, like it's going to be impossible to get a derivative. This is totally undefined. Now, I'm not giving this to you as I'm just trying to trick you, ha. It's the chain rule's all in here, and the way we took derivative is fine, but the definition of the function is invalid. Okay? All right. We're going to still box this. We're going to leave it. All right? This is where I would leave it because, I mean, technically speaking, not in this class, but you can have a square root of a negative number, just not here, right? All the calculus that we do, complex variables, and so we will wave our hands at it. On a test, I would never give you something like this. I would just change that to something like 1 minus x squared in there or something, and then it would work. You wouldn't have any problems. All right, moving along. Derivatives of the inverse trig function. So I showed you just now the derivative of the arcsine, right? Derivative of arcsine. But, as you might imagine, there are all the others, right? I'm not going to go through those. But here are all the others right here. All the other inverse trig. The derivative of arc cosine is exactly the derivative of arc sine with the exception of what? A negative here. The derivative of arc tangent. This is a big one. It's going to come up a lot this class. The derivative of arctangent is 1 over 1 plus x squared. Burn that into your brain right there. That look. You have 1 over 1 plus variable squared. That is going to peek its head out a lot this semester, so the sooner you start getting acquainted with it, the better. We'll go backwards here. Arc cotangent, same as this one with a negative. And then these don't come up as often, arc secant and arc cosecant, but here are the derivative formulas. Questions? So given that, let's see if we can figure out example 4. Y is the square root of natural log of arctangent of x. So I just want the derivative here. This is chain rule, isn't it? If we look at this as a function, the way we do chain rules, we start with the outside and work our way in, right? That's the way chain rule works. So what is the outer function? What's the last thing happening here? The square root of all that junk, right? So I'm going to try and do this as, like with the expectation that you've done a lot of chain rule in Cal 1, so you're familiar with what I'm doing here. If this is a struggle, you need to probably work on it. Come talk with me. Okay, derivative of the square root of something is, I'll do it both ways. 1/2 times whatever was there to negative 1/2, right? That's what some of you said you saw. What goes in there? ln arctan x, right? That's what goes in there. Now, that takes care of the square root. Now, go inside the square root. The next thing happening is the natural log. So now I need to say times the derivative of natural log of something. So what is the derivative of natural log? It's 1 over whatever was in there, right? So 1 over arctan. Hey, wait a minute. If you have a negative exponent, doesn't that mean move it up? No. Not here, okay? This is one bad part of math notation, is that we use this -1 symbol to mean two different things. When the -1 is attached to a trig function like that, it means inverse. When the -1 is sitting on an x by itself like that, that means it's move it up, right? So just don't confuse the two. So we have to leave it like that. All right, I'm done with, I did the square root, I did the natural log. Now I move inside the natural log. What's the derivative of arctangent of x? 1 over 1 plus x squared. Now that's like the raw derivative here. You could start cleaning things up. Let me see, if I clean it up, I'd have a 1 on top. On the bottom, I have a 2. I would have the square root of natural log arctan x. I'd also have an arctan x down here. I'd also have the 1 plus x squared down there. So that would be your derivative. And just leave it like that. You could shuffle things around. You could put that arctan up here next to the 2 and move that 1 plus x squared up, but that's good enough. Questions? Next one. Example 5. All right, arc sine of xy squared plus 1 plus xy. We're asked to find dy dx. Anybody see the issue we have here? We have a y on both sides. And there's going to be absolutely no way we're ever going to be able to isolate that y. You should have ran into this in Cal 1. And the way we got around it is by using implicit differentiation, which is what we used a little while ago. So what I'm going to do is I'm going to take the derivative on both sides of this equation implicitly with respect to x. And I'm going to apply any rules that I need to as I go. So let's see how much you remember here. What is the derivative of arc sine of something? It's 1 over the square root of 1 minus what? X squared. But in this case, we have more than x inside that, don't we? We have xy squared squared. Does everyone see the formula that we had being used there? I'll put it over here. The derivative of arc sine of u is 1 over 1 minus square 1 over the square root of 1 minus u squared. But in our problem, the u is what? Xy squared. Follow? Now we're not done because chain rule says you've taken care of the arc sine part. Now go inside and take derivative of what's in there. So I need to take derivative of what's in here. So I have to use the product rule in there, right? Because I have x and I have y squared and they're separated by a product. So I need to attach to this product rule. So I'll draw my little dot between, that's the way I did it. And whenever I do a product rule, I do it this way. You can, I don't know, hopefully you learned this way. I do the derivative of this one times this plus derivative of this times this. You may do it backwards. As long as you get them, it's okay. So I'm going to do derivative of x, which is 1, and I'll put it there, times y squared, plus derivative of y squared. Tricky, be careful here. 2y dy dx, good. And then times x to finish off the product rule. Is it okay to write y prime here? I'm okay with that, all right? You could write dy dx or you could write y prime. So am I done with the left side? This left side? Yes, right? I took derivative arc sine, here it was, following the chain rule, derivative of what's inside is product rule, I'm finished. So I move to the other side, so equals, derivative of 1 is 0, plus another product rule, right? So derivative of x is 1 times y, plus derivative of y, which is dy dx, times x. That's all I'm going to do on this problem because we have dy dx here and here. So what we could do is we could start shuffling things around. We would distribute this through. We would bring all of our dy dx terms to one side of the equation. We would take everything that doesn't have dy dx to the other side of the equation. We'd factor out dy dx. We'd divide through, and we would get our answer. Just, you know, go review implicit differentiation if you need to on how to isolate that. But the part of the problem that was the most challenging, I think, is over. It's the derivative has been taken, all right? So, dot, dot, dot. Questions? Are we at example 6 already? Example 6. A rocket is fired straight up with a speed of 1,000 miles, a speed of 1,000 miles per hour. So imagine this rocket moving with a constant speed of 1,000 miles per hour going up, all right? An observer who is a mile away from the launch point is tracking the rocket with binoculars. At the moment the rocket is 3 miles high, how fast is the observer's angle of inclination changing? What is that in degrees per second? This is a related rate problem. So I'm going to start with a picture. Here's the ground. Actually, I think I'll do 2 pictures. Here's the ground. My rocket, let's say, took off from that point. My rocket is traveling straight up like this, right? I have an observer who's sitting over here who I'm going to represent with a different point. I know that observer is exactly 1 mile from the launch point, right? So I'm just going to label that 1. I know that the rocket is moving with a speed of 1,000 miles per hour. Now, I did not label this side over here 1,000, because the 1,000 isn't the length of this or anything, it's the actual rate of change of that, right? So we can imagine that the rocket's up here, right? Here's my rocket, that blue point. I'm not being artistic. Like I could go and show off right now and draw a really badass rocket like that, but I'm not trying to show off, all right? That point is my rocket up there. I can do more. I mean, you want flames and stuff? I got it. So there's my point, there's my observer, there's my launch point. Or there's the tip of the rocket, launch point, and observer. That's kind of the picture of what's happening, right? And it wants to know is they're tracking this at exactly the moment that the rocket is how high? 3 miles high. How fast is the angle of inclination changing? The angle of inclination is the angle between the ground and the rocket. So let me label that in my picture. Assuming the guy's tracking pretty well here, the angle would be this, right? Theta. And that theta is changing, right? Now, there's a specific moment in time when we want to say, right then, how fast is it changing? But in the general picture, as the rocket is launched, that angle is changing the whole time. And it's not necessarily constant. Maybe faster in the beginning and slower at the end. Now what? Find what? Okay, 3 miles here. Well, be careful. Hold on. The reason I haven't done that yet is this. Whenever I'm doing related rate problems, I always like to draw two pictures. I like to draw a picture of what's happening when things are changing, and I draw a picture of what's happening when everything's stuck in time. And remember that, look, if I'm running across the room right now, right, and I say right there when I snapped, how fast was I going? Then I would have had a speed, right? But if I run across the room right here and then I go like this, and I say, how fast am I going? It doesn't make any sense, right? That's trouble with related rate problems, was that you can never fix anything in time until after you do a derivative. So I don't want to label that 3 yet, because that fixes everything. So I'll do that on my other. I hope that made any, some sense at all. What do you want to call that side over here with the rocket? R for rocket? That's fine. Do you agree that theta is changing as the rocket goes? Do you agree that R changes? Yes? Does the 1 change? No. So that's a good picture of what's happening as the rocket's moving. Now let me compare that to the picture of the instant in time that we're talking about. The instant in time, now I can fix this at 3. This, of course, is 1. And therefore, the angle is not just any angle, right? You could actually figure out what that angle is, couldn't you? It's not changing anymore. It's static. It's stuck, right? I'm not going to do it right at this moment, but we could figure it out. So the way that we did related rates, again, in Cal 1, is that we started by finding an equation that relates the variables that we're interested in together. And we write down what information we have. This 1,000 miles per hour is a rate of change. It's a speed. It's a velocity. That means it's a derivative. What is it the derivative of? It's the derivative of which variable? It's dr dt, right? It's the rate of change. It's the rate of change of r, because we labeled it r, right, with respect to time. That is the 1,000. What is it that I want to know? What is it that I'm trying to find? What is the it's asking the rate of change of the angle, right? So we want d theta dt. So d theta dt is what we're interested in, right? When is it that we want to know this? At this particular instant in time, right? So I want to know this when, what's 3? R is 3. Okay, so that's a summary. Here's what we were given, right? I know the rate of change in R. I want to know the rate of change of theta, and I want to know it exactly at the moment that R is 3. So what I like to tell my students in Cal 1 is you now need to find an equation that connects r and theta together. Any equation you can think of. And I hope that you would look at this and say, I've got a right triangle here, and there's a way to relate the angles to the sides. I know these two sides, right? So what trig function relates the opposite and adjacent side together? Tangent. So I could write this, right? Tangent theta is r over 1. Yes? Now in Cal 1, you could at this point just take the derivative implicitly on both sides. But let's use a little bit of what we did today. Because so far, this is nothing new in this class. What I'm going to do is use the cancellation property right now. Because I'm interested in knowing d theta dt, right? So wouldn't it be real nice if this left side of the equation was just theta? Right? So I'm going to take, on both sides of the equation, I'm going to take arctangent. Take arctangent on the left. I'm going to take arctangent on the right. The left side becomes theta. The right side is just arctangent of r. And that's the equation I'm going to work with. That's the one I'm going to take the derivative of. And I'm going to do implicit differentiation. I'm differentiating both sides of this equation with respect to what variable? To t, time, right? So take derivative of the left side. What's the derivative of theta with respect to time? d theta dt, which is what we want, right? It better appear, right? Because that's what we're trying to find. And then on the right side, I'm trying to find the derivative of the arctangent of something, which I said, you remember, start burning that formula into your head? 1 over 1 plus x squared, but in this case, x is r, right? Chain rule. Now you have to go inside and take derivative of r. What's the derivative of r with respect to time? dr dt. So we're done. We just need to plug things in now. Now I can fix everything in time. So d theta dt is going to be 1 over 1 plus r squared. Did we know what r was? Now we can say it's 3, right? So we plug 3 in here, we get 9, that's 10, that's 1/10. 1/10 times 1,000, right? Which is going to be 100. 100 what? What was our measurement of speed in for the rocket? It was miles per hour, right? This is giving us a rate of change of theta. Nowhere in the problem have we used degrees, though. And in all math, when you deal with angles, you're always in radians unless somebody forces you out into degrees. So right now, this 100 is 100 radians per hour, all right? So we're looking at the angle. When I do related rate problems, I never carry my units. Like some instructors, they write down here 1,000 miles per hour, and then they write down the units down here, and then they start canceling things. I always just look, what's theta? In this problem, what's theta? Well, it's an angle. It's measured in radians. Everything's in radians, okay? And then I say, what's time? Well, it was hours, right? Miles per hour. So since time is in hours, I know that this will be rads per hour. 100 radians per hour is my instantaneous rate of change. We're almost done, and I'm out of time. The last thing was, what is this in degrees per second? Can I go 1 minute over here? Thank you. I appreciate that. 100 radians per 1 hour. I want to convert that to degrees per second. So let's get rid of radians first. This is just, what do they call this? When you cancel units and stuff like that? Unit conversion stuff? Dimensional analysis is what it's called. So what we're going to do here is get rid of radians. So I need a connection between radians and degrees because I'm trying to get it to degrees. I know that there are 180 degrees in how many radians? Pi radian? Pi is 180 degrees, right? Okay. All right, so pi radians is 180 degrees. I can get the rads to cancel, but I have to multiply by 180 and divide by pi. Okay, then How do you get from hours to seconds? Is that what we wanted? How many seconds are in an hour? So I put hours up here because I'm trying to get the hour on the top to cancel with the bottom, right? 1 hour is how many seconds? 3,600 seconds. So your rads are going to cancel. Your hours are going to cancel. So multiply across the top, 100 times 180. Then divide that by pi times 3,600. Whatever that answer is your answer in degrees per second. I won't finish it. I'll let you. There is a homework assignment. The expectation when you leave class is that if I give a homework assignment, that you will complete that by the next time we meet. I know for some people that's not realistic, but that's the expectation. I mean, like if you work a lot or something like that, you want to use the weekends to do all your work. I get it, but my expectation is that you will have that done by the next time we meet. I do not collect homework. Okay, the answers, most of them are online already. Most, not all. And so it's really just, you do the homework, and if you have questions, I'll answer questions at the beginning of class. But if I get a sense that people aren't doing their homework, then I'll just go around and I'll say, let me see your homework. You don't have it, you won't get a quiz grade. So bring your homework every time, all right? So next time we meet, bring it. I may not look at it, I may. All right, everyone. Hope you have a good rest of your day. Oh, sign-in sheet. I didn't pass it around. Let me see. 2, 3, 4, 5, 6, 7, 8. Hold on. 4, 5, 6, 7, 8, 9, 27. I think that's the whole thing here. Perfect. All right, that doesn't happen very often. Everybody is here. So we don't need to take attendance.